Alright, now let's do our first problem regarding the review of of static concepts. Okay, so for this problem is taken from the textbook of Hibbeler. The title is Structural Analysis, 7th edition, and it's taken from example 2-9. Okay, so the problem says that we are to determine the reactions on the beam in the figure. Okay, so here's the figure, and um, this is the beam, although this is not a straight beam, but the load is in flexure, so that's why it's still a beam. It's still referred to as a beam, and it says here that assume A is a pin. Okay, so this is our A. So this is a pin support, and B is a roller support. Okay, so right here in the figure we have this distance from point A to this midpoint. This is 2.1 meters, and from this midpoint to this, actually it's not a midpoint. Okay, so from this point to point B, that is 0.9 meters, and from this point going upward, this is 1.2 meters. Okay, so this is our beam, and it is under this this is subjected to flexural loads of 7.5 kilonewtons per meter. Okay, so we just have to find these support reactions. What's the value, or what's the magnitude of this magnitude and direction of this support at B and support at A? So basically, we just have to apply the equilibrium equations. We just have to recall the reactions present for this type of supports, and also for the idealizations of the loads. Okay, so for the solution, okay, so number one is, let's first check if this is a determinate problem. Okay, so we have two reactions right here, 2 plus 1, so this is 3, and we have three equations of equilibrium. So therefore, this is a determinate problem. Terminate. Okay, problem. Okay, so therefore, let's now draw the free body diagram of this beam, or the loading diagram rather. Okay, so draw the loading diagram. By the way, what is the difference between the loading diagram and the free body diagram, or this diagram? Okay, so the difference is that for a loading diagram, we'll only have to expose the loads, whereas this one, we also draw the simplifications or the idealizations of the supports. Okay, so right here for the loading diagram, let's just expose only the loads. Okay, so we have here, this is point A, then this is, let's say this point, this point. Okay, and then right here we have something like this. Okay, and our external load is this one, and this is 7.5 kilonewton per meter. And recall that in your statics, that whenever we have a distributed loadings, then there is also an equivalent resultant force that's acting at the centroid. So if this is our uniform distribution, it's just a rectangular, then this resultant force is just acting along this at this centroid. Okay, so basically we just have to multiply this force by this length, because this is kilonewton per meter, so we have to multiply this in terms of we have to multiply this with length, so that we can only obtain the value of kilonewtons. Okay, so right here we have AX and AY. So our support reaction at A, so we have AX and oh sorry, this is AY and this one is AX. And right here, okay, so this is our B, right? Okay, so but this is not purely along X or purely along Y, so let's just write BXY. Okay, this is purely Y, so this is AY, this one is purely X. Okay, and now let's draw, or let's input the length. So we have here, this is 2.1 meters, and right here this is 0.9 meters, and right here this is 1.2 meters. Okay, so since we have this distance 0.9 and 1.2, then I can actually find the angle here, right here. Okay, so if this is the angle, then basically this angle is the same as that angle. Okay, so in order to find this, we only have to apply the trigonometric um, formulas. Okay, so let's write here, applying the trigonometric identities, or let's say formulas in solving for the angle. Okay, so our angle is just simply tangent theta is just equal to 1.2 all over 0.9, so theta is equal to 53.13. Okay, however, what I want is this angle, right? So what I want is this angle. So let's say this angle is let's say this is alpha. Okay, so alpha therefore is just simply 90 minus this theta, or phi. So we get 36.87 degrees. Okay, so we have this angle 36.87. Okay, so therefore you would also notice, by the way, that these reactions, these roller support reactions, um, this is this is not purely X or purely Y. So therefore, uh, we can just simply represent this in terms of its components along X and along Y. Okay, so if that's the case, then if we draw it here, okay, or let's write the line labels. This is what we call as the line labels. So drawing the components of BXY. Okay, so this is our BXY, and of course the components will be along X and along Y. So since this is our theta, or this is our angle alpha, then with respect to this angle alpha, this one is BXY cosine alpha, and then this one is BXY, okay, BXY sine alpha. Okay, so now I guess we are good to go. So let's apply now. Okay, applying now the equilibrium equation. Okay, the equilibrium equation. And so let's first take the summation of moment at A. So we'll take moment at A. Right, so if you take moments at A, by the way, this one is 7.5 times 2.1. What we get here is a value of 15.75 kilonewtons. Okay, so summation of moment at A, and let's say the clockwise direction is positive, is equal to 0. Okay, so from this, okay, so this is my my center of moment. Okay, so this force, this 15.75 is acting, okay, this one is acting downwards, so that's actually producing a clockwise moment with respect to A, and the distance is 2.1 divided by 2, which is just 1.05 meters. Okay, so let's write it here. 15.75 kilonewtons times 1.05. Okay, so what else? Okay, what else? We have also the x component. So the x component, it's producing a counterclockwise, so that is minus. Okay, we can write minus, or I can just simply write it in the other side. Okay, so this is bxy, right? So this is bxy, right? Bxy cosine theta or cosine alpha, okay, times the moment arm. Okay, so this is the force, this bxy cosine theta times the moment arm of 1.2. Okay, plus, okay, another one, this is bxy sine alpha. Okay, so the y component, uh, the the distance. Okay, so this the y component produces also moment that's counterclockwise. All right, so it's going counterclockwise, and the moment arm is from this point, from the center of moment to this point. This is 2.1 plus 0.9. This is just simply 3 meters. Okay, now if you do the math, what you get is a value of bxy, or let's just say b, is just equal to 5.99 kilonewtons. Okay, so this is our value of b. Okay, and if we take summation of forces along y is equal to 0, okay, so we have the forces along the y direction is ay, this one, this 15.75, and the vertical component of the bxy. So right here we have ay, right? Ay minus this 15.75, okay, plus the b sine theta. So this is 5.99, right? Sine theta or sine alpha, okay, is equal to 0. So what you'll get is 12.15 kilonewtons. And if you apply the summation of forces along x equal to 0, so what you get is the forces along x are just ax and the x component of bxy. So this is ax is equal to bx is equal to simply b. Actually, the x component, sorry. So this is bxy cosine alpha. So this is 4.79 kilonewtons. Okay, so just for review, what we did is we first check if the problem is determinate, and then we draw the loading diagram to just simply expose the loads. Okay, so we can, if we have a distributed loadings, then we can also express this in terms of its resultant force. Okay, so once we have all that, we have the geometry, then we can actually apply the equilibrium equations, and we apply the summation of forces along, the summation of moment along z, and the summation of forces along y, and the summation of forces along, summation of forces along x and y, we equate it to 0, and then we can obtain the support reactions. Right, so we'll do another problem regarding these equations of equilibrium. Okay, so for our second problem, we have this problem taken from the textbook of Hibeler, the same textbook as from our problem 1.1, and this one is taken from the example 2-10. Okay, so the problem says that there's a compound beam in a figure and it's fixed at A. So this is our beam. Compound beam means that we have member 1 right here. And so this is member 1. And then we have member 2. So why is it we have member 1 and member 2? Simply because of this pin support or internal hinge. Okay, and in terms of dimensions from point A to point B, this is 6 meters, and from point B to point C, this is 4.5 meters. Now, this compound beam is subjected to a distributed load from point A to B, that's 6 kilonewtons per meter, and an external moments of 8 kilonewton meter. Okay, so this one is fixed, right? Fixed internal hinge, and this one is a roller support. Okay, so now let's do the solution. Okay, so the first step is to determine if we have a determinate problem. Okay, so recall that, or let's write here the line labels. Determine the determinacy. Okay, so we have support reactions here. We have 6, right? Or let's write the equation R is equal to 3n. Okay, so the reactions here are 3, right? Since this is a fixed support, so one x, y, and the rotation. So 3 plus 2, so that's 5. Okay, plus 1, so this is 6. Okay, so again, 3 support reactions, 2 support reactions right here, and 1 support reactions in this roller. So we have 6. Okay, and for the number of members, we have 1 and 2, so we have 3 is equal to 3 times 2. So this is determinate, right? Determinate problem. Okay, so the next step is to draw the loading diagram. Okay, so right here we have a fixed support. So this is 6 kilonewton per meter. Okay, and what else? Right here we have, let's say this is AX, and then this is our AY, and this will be our moment, A sub M, moment at A. Okay, and right here we have a moment of 8 kilonewtons per meter, and we also have CY. Okay, so this is the let's say this is figure 1, because we are just drawing the loading diagram of the entire structure. But we can also, since this is a compound beam, then we can also apply the loading diagram for just member 1 or member 2. Right, so right here, let's say this is member 1, and right here this is member 2. Okay, so for member 1 we have these loadings, right? And this is 6 kilonewton per meter, and whenever we have a distributed loadings, then we can represent it by this resultant force. Okay, so right here we have we have a reaction. We have two reactions right here. So let's say this is bx, then this is by, and right here we have ax, right, ay, and a moment along a. Now in terms of the internal hinge, now with respect to this member, this is the direction, but with respect to this member, it would be the opposite direction, right? So this is bx, by. Okay, and right here this is cy, and we have a moment of 8 kilonewtons per meter. Okay, so now let's by the way, how do we know if the direction of bx and by is along this direction or along that direction? We actually can just assume, or we can just inspect. But if it's hard to inspect, then we just have to assume a direction, and then if we get a negative value, then that means that the direction is the other way around. Okay, so right here, let's applying now the equations of equilibrium. Okay, and we will apply the equations of equilibrium in from which figure? Let's say this is figure 2, and then this is figure 3. Okay, so that's the good thing if we have line labels, and we also have um, labels for the figures. Okay, so if we apply right here, we can also obtain the value of cy, right? It's also possible if we apply the summation of moment at a, then we can find the value of cy. Or right here, if we use figure 3, then we can also apply the value of we can find the value of cy. So let's say applying now the equilibrium equations at figure figure 3. By the way, right here for figure 2, we cannot it would be not sufficient to be able to solve the unknowns, because if you apply the summation of moments along a, we have two unknowns. Or actually we still have we can have also one unknown, but also because this is 0, and the by, this will have a value. Okay, so by the way, we forget that this one, that's times the distance, 6 meters, this is just simply 36 kilonewtons. So right here, so this is 36. Okay, so we'll use figure 3. So summation of moment at b is equal to 0. Okay, so if we take summation of moment, we only have the moment from this concentrated moments and the moment produced by the cy. Okay, so this one is clockwise. The cy produces a counterclockwise, so we can just write simply 8 kilonewtons is equal to, right, let's write the units, is equal to cy, right? Then what's the distance? Right, so this distance, this is 4.5 meters. Cy times 4.5 meters. So Cy is equal to 1.78, right? 1.78 kilonewtons. Okay, so the next is we take the summation of forces. Let's say summation of forces along x equal to 0. So the forces along x is only bx, so that means that bx is equal to 0. And if we take the summation of forces along y, right, so along y, and let's say we'll take upward direction as positive, then the y direction is just cy and by. Okay, so by is just equal to cy, which is just equal to 1.78 kilonewton. Okay, so now we have the values here, the bx, by. Then we can just substitute above values to figure 2, right? Figure 2, and apply the equilibrium equations. Okay, so if we apply, if we apply right here, what we get is summation, or if we apply the summation of forces along x is equal to 0. Okay, so that means that ax is equal to bx is equal to 0. And if we apply the summation of forces y, right, summation of forces y is equal to 0. Okay, so the forces along y is ay, by, and this 36 kilonewton resultant force. So that means ax, okay, or ay is equal to or ay is equal to 36 minus 1.78. So this is 34.22 kilonewtons. Okay, and then lastly, if you take summation of moment at A, okay, summation of moment at A is equal to 0. Okay, so what we get, okay, summation of moment at A is equal to 0. So the moment will be AM plus 36 times the moment arm. This is actually 3 because the entire length is 6. So 36 times 3 minus, right, this one, the by that's producing a counterclockwise moment. This is by times, okay, the moment arm, which is equal to 6. This is 0. So therefore a sub m is 97.32. Actually, this will be negative, right? This will be negative. So that means that instead of having a clockwise rotations, our AM is counterclockwise. So this is 97.32 kilonewton meter and counterclockwise direction. Okay, so lastly, we'll do a summary of answers. Right. Summary of answers. Okay, so right here we have ax, ay, and the moment, and we also have bx, by, and cy. Okay, so for ax, the value is 0. The ay is 34.22. This one is 97.32. Right, but what's the direction? Okay, so this one is upward. This one is counterclockwise, and bx is 0. By is 1.78. Okay, but the direction is that depends upon which member are you talking about. Okay, so 1.78, this is upward. Okay, so for a brief review, what we did is just simply we checked the determinacy, and then we draw the loading diagrams of the entire structure and also the half of the structure and then the other half of the structure, and then we apply the equilibrium equations. Okay, so I guess we'll do another problem for these equilibrium equations in the next video.